Hello, can you hear me? Hi, good morning. How are you? And yeah, I'm well, thank you. And so, okay, fine. I'm online. So whenever there are enough participants, we can start. So I'm online, and I hope that things will be all right. So, all right. Thank you. I'm online. Just call me when people come.
Dear participants, please keep on mute.
Hello and good morning to everyone, and thank you for inviting me to speak in this FDP. So I'll start discussing about quantum computing from the beginning and go up to certain applications, if not in quantum computing, but in the context of quantum communication. So let me switch off my video and share the screen. So please tell me whether you are able to see my screen. Introduction to quantum computing. Are you able to see my screen? Dr. Gantayat? Hello.
Yes, sir.
You're
We
able
can
to
see.
see my screen. Wonderful. Thank you.
Thank you, sir.
So that's what I wanted. So I'll be also. And are you able to see what that I'm writing on my screen? So I can like. Can you see that I'm what my writing on the screen? Hello. Visible. Okay, wonderful. So that's what I wanted to check. All right, wonderful. Hmm. So I will start talking about quantum computing from the beginning. So the first word. So first of all, I'm not talking about physics. I'm talking about how we look, how we can look at quantum computing without talking about physics. So the first thing that we come across is called a qubit. Now, now let us go back to our usual computing. So first thing that we come across when we talk about the computing, our usual computing, classical computing, that is a bit. That is a bit. All right. Now the question arises: what is a bit? Now, a bit, we can look at bit as a some kind of object where we can store, which can remain in two stages, two states. So a bit can be realized by many physical systems, but whatever we do, it has to be something, some kind of object which can remain in two states. So we can even say that bit is a set of two different symbols, 0 and 1, and at each time it will be, whenever we observe it, it is either in the state 0 or in the state 1. So this is how we might look at bit. Now, if we go to the domain of electronics, then the people in electronics will think about how to realize a bit on a machine. So we are not talking about that. And of course, if we uh, in the end we will have to talk about those things, like for actual realization. I mean, if someone is talking about doing something in a completely, but we are not trying to do anything completely right now. So we are only talking about the ideas. So bit is an object which can stay in two different states. So if I say that I have got an 8-bit machine, that means that element of memory has 8 bits, and there I can store a sequence of 8 zeros and ones. And now if you if we try to recall like what happens there, now you will recall that there are things that I expect that I can do on a machine where I'm storing the bits. First of all, for some reason we assume that whatever we are storing will not be changed. Like for example, if you are writing a, for example, I mean, like I have written these slides, prepared these slides, and I have stored them on my memory, and then I have got reasonable faith on my machine that these are not going to change, and really it is not going to change. And then I know that I can write something and I can read. So I have an idea of writing and reading, or probably that we can say the read and write. So I can read and I can write. And another thing that we take for granted is that when I am reading a bit, the bit itself will not change if I do not change it. So when I read a bit, it will not change. So these are the things that we take for granted. We also know that we can copy a bit. So suppose I have got a uh, something like this 10101100. Suppose it's a 8-bit segment. I know that I can very easily copy this and prepare another 8-bit segment having the same elements, and like that's a copy of that. So when we are talking about classical computing, then these are never issues for us. So, um, but when we talk about quantum computing, it is very surprising that these very normal things that we take for granted become issues. So that we will be talking about very soon. Now, let me remove this portion and then I'll talk about what happens when we talk about something called qubits. So what we know so far is that quantum computers are again some kind of computers, and therefore it must have some basic elementary unit of information. In the case of a quantum computer, that thing is called a qubit or a quantum bit. So our discussion starts here. So we have a quantity called quantum bits, which is called a qubit in short, taking this q from quantum and bit from bit. So it's a qubit. Now, I'll ask now, of course, we ask a question that what is a qubit? A qubit is a quantum system which can be in certain states. So see, I can. We do not talk like this when we talk in classical computation. So we don't never say like this, but it is indeed true that I can say that a bit is a system which can remain in two states, either it is 0 or 1. In the same way, I can say a qubit is a quantum system that can exist in certain states, and a state of a qubit is represented by a pair of complex numbers whose modular squares are is equal to 1. All right. So if I take a number like this, 1 0, if I take a number like this, then modular square of 1 is 1 and modular square of 0 is 0. So I have got 1. But if I take a number like this, so let us see whether I can generate something like this. So I and 0. So I see modular square of I is 1 and modular square of 0 is 0. So I've got 1 again. But I will see that I can have many other ways of writing a qubit. So most famously, let us say if I take something like this, 1 by root 2, 1 1, or 1 minus 1. So it is a pair of complex numbers. Well, although they're real, ultimately they are also complex numbers. So I get this. And now if I take mod 2 square and minus 1 by root 2 square, so I get 1. So these are all qubits. So at this point, you will ask that, okay, fine, I know how to realize a qubit on a machine. Now, how to realize a qubit on a quantum machine? Now, this is a question that is precisely a question that people who fabricate quantum computers or quantum communication channels ask, and so this is a specialized area. It's a very important area, but today we are not discussing about the realization of qubits on a machine. So we are assuming that it is possible to design systems. It is possible to design quantum systems. It is possible, we are assuming that, and it is in fact true, it is possible to design quantum systems, quantum quantum systems such that its state can be completely specified by a pair of complex numbers a b such that mod a square plus mod b square is equal to 1. So this is what we assume. Now there's a way of writing these states, so it's worth looking at that. So if you have, so I am assuming that since it's a pair of complex numbers, we have got two components. Each component can carry a complex number, and the number 1, 0 is traditionally written over here. So it's at this point is 1, 0, and this is written as ket 0. This particular so this particular symbol is called ket. This is called ket 0, and this is ket 1. So this is this point, ket 1, and therefore see that I can write any qubit state as AB, a general qubit state AB, as A into ket 0 plus B into ket 1, of course, because A into 1, 0 plus B into 0, 1 gives me A ket 0 plus B ket 1. And of course, their modular square summed up gives me 1. Now, I don't have to recall complex numbers here, and this is something that I've told you. Now, so we again come to the definition of qubits that I have already talked about, and so I'm not going to do that again, and we move forward. So, if we want to study quantum computing, we of course have to know what are qubits, and we will see that there are some limitations as far as qubits are concerned. The first of all, we will see that it is possible to create qubits. It is possible to create qubits having a particular state. That is possible. So if I can say that, okay, I'm considering one state like, let's say, so like ket 0 plus I times ket 1 divided by root 2. So this is 1 by root 2 ket 0 and I times 1 by root 2 ket 1. So there are physical processes by using which we can create quantum states like this, or like any one quantum state that we choose to construct. But what is not known, but what is strange is that there is a severe limitation as far as reading these states are concerned. For reading and copying the states are concerned. So it is not possible to read a quantum state as it is, and it is not possible to copy a quantum state. So these are the two things that are very important. It is not possible to read I'm putting it within quotes, there is a reason for it, read a quantum state and know its exact value. Okay. And secondly, it is not possible to copy a quantum state. It is not possible to copy a quantum state. Now these are very strange things. These are very strange things. And so after everything that is said and done, we are we have been told that quantum machines are amazingly powerful machines and they can solve problems that are very difficult to solve by classical machines and sometimes computationally infeasible. And we have got proofs for we have got techniques and algorithms coming up for the last 30 years telling us about those problems and how they can be solved by quantum machines. So that gives us a vision of a quantum machine that's all powerful, amazingly powerful machine with very little limitations. But despite the fact that these algorithms are indeed very powerful, we are up against a machine that has amazing limitations. So the limitation is that you cannot essentially read out a quantum state, or you cannot copy a quantum state. Wow, then one will ask a question, then what can I do? Now, what we can do is technically called measurement. Now, this is something that is, I will say, a measurement is processes are, let me try to find the exact word. I have always felt that measurement is always a bit of a neglected area because we really don't think that measurements are important, although they are important. So these are underestimated. So this is an underestimated area because as soon as I talk about measurements, now I think at least it used to come to my mind that, well, I do not want to read about measurements because what are measurements? That is measuring something, and of course we can measure something. Now, so what is so big deal about measurements? If you would like to know how algorithms work, not how measurements work, because of course measurements can be done. The point here is that when we are talking about quantum computation, this idea of measurement of a quantum state takes a central position. Now the question is that what do we mean by a measurement? So idea is that I cannot, if I am given a quantum state, it is technically a unit vector in the space of pairs of consisting of pairs of complex numbers. So the space is technically C cross C, that is C2, and I'm given a vector here, which is I write as AB, and using the ket notation, I could also write AB as A ket 0 plus B ket 1, and I agree that this portion is A0 and this portion is 0B. It's not a problem. Now, measurement simply means that, that simply is again within quotes, so it is not simple or easy. But the measurement means that you have to choose a orthonormal basis of C cross C. For example, 1001 is an orthonormal basis of C cross C, and the inner product is the usual inner product on C cross C, and just write the vector in terms of that basis and take these coefficients, and a measurement process is always related to a basis. With respect to a measurement, there is always a basis and orthonormal basis. And if we expand the vector as linear combination of those basis elements, then the mod square of the coefficients gives me the probability that I will observe that basis element as my measurement result. So if I have got, so let us fix a point here. Let me remove this portion. So ultimately this whole thing boils down to something like this, that suppose I have got a vector, a quantum state, and we will be writing a quantum state in this way, ket psi. So this is read as ket psi, exactly this. So this quantum state is, let's say, 1 by square root of 2 ket 0 plus 1 by square root of 2 ket 1. Suppose I am measuring this quantum state by using the basis 0 ket 1. So measurement means there is a basis, and now what is the coefficient corresponding to the ket 0? That coefficient is root 2. So take the square root 2 mod square half, and so the probability is half that the measurement result will be ket 0, and similarly the probability is half that the measurement result is ket 1. It is amazing because it is amazing. So I don't have a fixed measurement result. It can be either one of them. Just think about this. I'm coming back in 2 minutes. Really? Yes, so I'm back. So this is the point that we ought to remember. So the idea is that this is like, if there's a quantum state, we can measure. For the measurement, there is a basis. and the measurement result can be any one of the elements of the basis, and the probability of obtaining these results is can be calculated by looking at the coefficient of the expansion. So for example, I think I have got some results here. So let us see whether we can kind of try to figure out something from here. Yeah. All right. Let us do some calculations. And like for example, if I've got a basis like this, then what will happen? Like for example, my quantum state is 0, get 0, but my basis is this. Then what will happen? Then what I have to do is this, that I have to get 0 is what? Get 0 is 1 0, and this basis is given in this way. So I have to write 1 0 is a times a by square root of 2 1 1 plus b by square root of 2 1 minus 1, and so it is going to be a by square root of 2 b by a by square root of 2 plus b by square root of 2 minus b by square root of 2. All right, so I'll be having something like this. So wait a moment. So I'll be having something like this: a plus b by square root of 2 and a minus b by square root of 2. So I have got a set system of equations, and that is equal to a plus b by square root of 2 equal to 1, and a minus b square root of 2 equal to minus 0. Right. So because this is the equation, right? So this is a system of equations. So now I can say that means that a plus b is equal to square root of 2 and a equal to b, and therefore twice a is equal to square root of 2, and therefore a equal to 1 by root 2. So I know that I will be writing 0 as as what? Is it correct? Or have I made any mistake? Twice of, so a comes to be 1 by root 2, yes, but then what happens? So then if I put it like this, so it is half of 1 1 plus half of 1 minus 1. All right, but it is not. Is that 0? Yes, that's all right. Like this. Wait a moment. Um, but then I don't have. I probably have made some mistakes over here. Wait a moment. Let us do this calculation once more. So if I want to write this, then a and b are 1, not is square root of 2, and therefore wait a moment, where have I made mistake? It can't happen. So let us do it again. So it's actually, it ought to be ought to be square root. No, that also doesn't work out. So let us see whether I have made a mistake or not, because any one of them must have occurred. And let's see. Wait a moment. What is happening? So suppose I want to write 1 0 with respect to this basis. Then what will happen? This is a by root 2 1 1 plus b by root 2 1 minus 1. Alright, so what does it mean? So this means that we have 1 by root 2 and a plus b and a minus b. Now that means that 1 by root 2 a plus b equal to 1. Look like I'm fine. And then, oh yeah, okay, I have understood the trouble. Yes, it's all right. So indeed, a plus b is equal to root 2, and a minus b is equal to 0, and therefore we are correct in saying that a is 1 by root 2 and b is 1 by root 2. All right, so there is no problem there. Now our basis is this, basis h is this 1 by root 2 1 1 comma 1 root 2 1 minus 1, and let us suppose we write it like this, ket plus and ket minus. So that means that I can write this ket 0 as 1 by root 2 times ket plus plus 1 by root 2 times ket minus. So see, if we have the basis element, if my basis element is ket 0 and ket 1, then how do I write 0? Ket 0 is 0. But if my basis element is ket plus and ket minus, then how do I write 0? 0 is 1 by root 2 ket plus plus 1 by root 2 ket minus. So if I measure with respect to this basis, that is, if my basis of measurement, sorry, a measurement basis is this, then I will always get ket 0. That is a very special case because the state is also ket 0. But if my measurement basis is ket plus and ket minus, then I will always get, then half of the times the observation results will be ket plus with probability 1/2, and observation will be ket minus with probability 1/2. So that is the idea of measurement. There are of course different notations, and there are easier ways of handling this measurement computations. For that we have to use Dirac's bracket notation that I'm not going to talk about today because it will take a lot of time. Now let us briefly look at what do we mean by superposition of states. We have already done that. So if I have a quantum state, and if that quantum state psi, ket psi, can be written in this way, and this is a basis, ket 0, ket 1 is a basis, it's an orthonormal basis of C2, ket 0, ket 1 is an orthonormal basis of C cross C2. Now if A is not equal to 0 and B is not equal to 0, both not equal to 0, then we will say that ket psi is in superposition, the state of ket psi is in superposition with respect to this basis. So it is a superposition of two basis states. And here we have to remember that superposition is not is dependent on basis. It is not basis independent. For example, if we take this state, then this state is in superposition of two states 0 and 1. But if my basis is this ket plus and ket 1, then of course psi, that is this one, is not a superposition. So that is also we have to remember that. And so I will skip all these things because it is a much more detailed lecture, and this the calculation part, and move directly to the quantum state transformations. Now, the point is that what we can do with quantum states. So what we have said that we can create quantum states. That is all right. We can measure and get the result as a basis element with certain probabilities, and we cannot copy. So these are the things that we can do with quantum states, but we can do something more. We can transform a quantum state, although we cannot measure it, in a sense that we cannot know the exact quantum state of a quantum system, but we can transform it. And these are different transformations. So for a quick look at these transformations, I'll quickly check these notation. Now see here, what is this? This is a way of writing. So I have been writing 0 as 1 0. Now there is something called conjugate transpose of a vector. So this is 1 0 dagger, and that is going to be the transpose and conjugate transpose. So all the elements must be taken conjugate. This thing is written as the bracket, the triangular bracket flipped the other way, and this is called bra 0. So this is ket 0 and this is bra 0. Now if I take a particular quantum state psi, which is equal to AB, where AB are complex numbers, this is ket psi, bra psi is going to be A conjugate B conjugate. So this is conjugate transpose. And if I take the bracket psi, so this is essentially the inner product. So this is going to be A transpose B transpose A conjugate B conjugate. So A conjugate A plus B conjugate B, and therefore this is A square plus B square. If I have got two different vectors psi and phi, so if phi is equal to C and D, then bra of phi is going to be C conjugate D conjugate. Now if I take bracket phi psi, bracket. So that is C conjugate D conjugate AB. So this is C conjugate A plus D conjugate B. So something like this we kind of can keep on getting. Now, if we flip these things the other way around, so for example, if we take the get first and then bra, then I get something like this, which are essentially matrices, and therefore I get matrices like this. And 2 by 2 matrices are going to be transformations over C2, and what is known by the theory of quantum mechanics that it is possible to implement for any uh, uh, for any unitary transformation on C2, it is possible to implement that on a machine. So it's possible to and operate a state with that transformation. So that's physics that tells us that. So any unitary transformation is an operator over a quantum state. So when we talk about writing quantum algorithms, then we have to discuss precisely this, that how to change the quantum states. So we have to talk about changing the quantum states by using a sequence of operators and get the results. Now, if you look at the classical computation, that is also what we do, because when we are talking about an algorithm, so algorithm will start with the input and then work on the input and gradually change the input to the output. So that's in a way the standard process. So that's what we will be kind of doing very often. Wait a moment. What has happened to this? Okay. So all right. So for example, here this is the identity transformation. So there is nothing in it, but this transformation is interesting. So if I apply this transformation on a qubit 0 1 1 0, and if the qubit state is given by AB, then I have got BA. So that means the qubit state A ket 0 plus B ket 1 transforms to the state B ket 0 plus A ket 1 একটু পরে কথা বলছি, একটা দিচ্ছি। তাহলে আমি একটু পরে করে নিচ্ছি 11টার পরে। তাহলে then it is like this. So it is flipping this. So for example, had we had a state like this 0, it would have flipped it to 1, and had we had a state 1, then it would have flipped it to 0. What does it mean? It works as the NOT gate. So this is indeed for a classical computation, it is a NOT gate. And like that, we have got many other transformations, and those are used in sequences and to obtain our results. Now, today in this lecture, we cannot talk about anything more than this, but of course, if we have more lectures, or if you take a quantum computation course, then you will find that a good part of quantum computation is how to apply a sequence of transformations over qubits and then measure to decide something. So that's the point here. Now I will move over to something called a quantum key distribution, which doesn't require a quantum computer, and which is a practical protocol. So I will be typically talking about a quantum key distribution protocol called BB84. And let us look at the setup. This is the setup. Now, let me take this white paper and try to explain what the setup again. So it is like this, that we have a problem in cryptography, that if Alice and Bob are communicating, and they first of all they have to agree upon a crypto system, and if the crypto system is symmetric, then they have to share a secret key. Alice and Bob must share a secret key. Now the question is that how are they going to share this secret key? Now there are different key distribution protocols, and we know about those protocols, so I'm not going to talk about that. Now around 1984, people found out that figured out that it's possible to share a secret key without a trusted third party, even if Alice and Bob uh, never met before. So this is the setup. So I will discuss about this setup in brief before closing the lecture. So it goes like this, that we assume that Alice is over here, and Alice has a quantum channel. So here it's let us say Alice has a classical channel with Bob. This is a classical channel, usual classical channel. And here they also have a quantum channel from Alice to Bob. And the attacker Oscar is sitting here, and the attacker has access to both the quantum channel and the classical channel, both. This is the quantum channel. So I think that probably I'll draw the quantum channel with another color. This is a classical channel, and the quantum channel, let us take the red color. This is a quantum channel. Oscar has access to the quantum channel also. All right, now they want to agree upon a secret key. Alice and Bob wants to agree upon a secret key. All right, they do not have any secure channel with them, but still they want to do that. Now, how they propose to do that? Now this is an algorithm to do that. It's a protocol to do that. It's a key exchange protocol. Right. So the idea is that Alice starts. So let us go one by one. So Alice uses a quantum or classical means to generate a random sequence of classical bit values. That is what Alice must do. So suppose Alice has generated 4 bits 0, 1, 1, 0, and suppose it is random. Now after that, Alice then randomly encodes each bit of the sequence. Don't read this polarization state of photons and all that. Just imagine that Alice can create these states, all these states. So what Alice does is that when Alice has 0, Alice either chooses this quantum state or this quantum state to send to Bob through the classical channel. She can choose either of them according to her wish and without telling anyone. She can do that. So for the time being, let us suppose that she is encoding 0 by gate 0 and 1. She has got choice. She can either encode by using gate 1 or this one. So suppose she uses this 1 by root 2 gate 0 minus gate 1. So this one. So like that. And now she sends this to Bob. Now when Bob receives, so what will Bob do? Now Bob doesn't know whether Alice has sent this, whatever Alice has sent. So what Bob does, Bob either takes gate 0, gate 1 as the basis of measurement, or this is essentially plus and minus, gate plus gate minus as basis of measurement and measures. Now by chance, if Alice and Bob's choice of the basis is same, then Bob will get back this. So for example, for the first 0, if Alice encodes by using this basis, that is 0 is encoded to get 0, and suppose Bob is measuring by using the same basis, then their measurement results will be same. But if it is different, let us say that Bob is measuring by using plus 1 and minus 1, then Bob will get plus 1 with 50% chance and minus 1, get plus with 50% chance and get minus with 50% chance. So 50% chance Bob will assume that Alice has sent 0, and other 50% it is 1. So Bob has a 50% chance of making a wrong guess. The idea behind the key exchange is that Alice does this and Bob also chooses the basis elements uniformly at random, and afterwards they exchange their choice of bases. So after everything is done, so see, over the classical channel, Alice and Bob check that Bob have received, so this thing is checked over the class. So Bob measures, so this is where Alice sends and Bob measures, and they choose the bases at random. Now the point is that if they choose the bases as random, both of them, then the probability is half that they have the same basis, and that is they have got the same measurement. So that means that the more or less they should be measuring, Bob should be measuring the qubit correctly half of the times. Now after this, over the classical channel, Alice and Bob check that Bob has received a qubit, read it as qubit, for every one Alice has sent. Then Alice and Bob tell each other the bases they used for encoding or decoding each bit. This is what they have to do. But from that, they will know, from this point, they will know that where they are correct, and then they will get the answer. So, for example, wait a moment. So, I don't have it here. So, so let us take this example. So, let us remove this from the screen, all these things, and then let us kind of see what happens over here. Yes. So the point is, suppose that the point is, suppose this is the first bit that Alice gets, and she encodes it as 0. And suppose this first bit that Bob gets, so Bob is getting this at Bob's end, and Bob has suppose Bob has chosen the right thing, or so suppose Bob has chosen the wrong thing. So Bob will get plus and get minus. So this is the basis that Bob has chosen. So Bob's result is either this or this. Now, if Bob's measurement result is this, then Bob will say that Alice sent 0, and otherwise Alice sent 1. But suppose that next one, Alice has this, and suppose that she is encoding this by using the other basis, and therefore it is this √2, which is get minus. And suppose that after getting the get minus, Bob measures with the same basis, get plus, get minus, then definitely deterministically he is going to get minus. So suppose a communication goes on like this, and suppose they only send 2 bits. So now, after sending 2 bits, suppose they exchange the basis. So Alice tells Bob that at the first instance she took this basis, and the second instant this basis, and in the second instance she took plus minus, and Bob tells Alice that in the first instance he took this basis, and in the second instance he took again the same basis. When they exchange the bases, then they automatically know that this is the place where they made the correct choice by chance, though. So that means the second bit is 1 for both of them. The second bit is 1 for both of them, and the first bit is chancy. So they may have got the same result, or they may not have the same result. They cannot guarantee that. So if this process is repeated over and over again, then they will come up, they will be able to agree upon a basis, upon a key. The point here is that at no point Alice and Bob sends exact key values there through the channel, public channel, therefore they are safe. This is the theory, but after this, there is a this is not the end of key distribution, and because after this there are issues that what happens when there is an intruder, that how to detect intruder, what the intruder can do, and how to exchange keys even if there is intruder. And for that there is a topic called key distillation, quantum key distillation, that how to work in the presence of intruders and error. Both are possible. You can have channel error, gate error, and measurement error, and you can have intruders. So how to deal with those situations and still exchange keys. So today I am not going to go on to these things, but there are different books on this, and this is an area which is practical. We have quantum key distributions working on at commercial level. There are companies that sell quantum key distribution machines, and there is a need for having a good idea about quantum key distillations and all that. So I'll stop my lecture here, and I welcome questions from your side. Yeah, so I see some on the chat. I see some questions. So there is. I'll try to locate that chat things. How to do that? Like there are proposals of searching techniques on data sets, but right now, if I am correct, there are no practical implementations of those things, because for data mining we have to have a quantum version of the data set. Now that's difficult to implement, but we can expect that we will see progress along those lines in the future, but we do not know how how far in the future though. But there is a definitely there is progress on quantum computers and on creation of large quantum states and all that. So data mining, of course, data mining and many optimization problems can be, people have shown theoretically that there are many optimization problems that can be done by using quantum computer. And as you know that IBM has a quantum computer, and IBM is also giving free access to a limited version of that computer, but it is a real thing. So there is research on this. I do not know what is a chemical channel. So a quantum channel depends on how we are implementing the qubits. So if the qubit is a photon, then I believe it's a kind of fiber optic channel or something like that. So I have no idea about how what a quantum chemical channel is. But so physical realizations, I'm not discussing physical realizations. I see. So physical realizations. I mean, we are not working on physical realization, so I can't tell you about that. You have to talk to people who knows quantum mechanics. Yes, there are some books on quantum machine learning. That's also an interesting area to work on. Yes, definitely. So everything is important. Like, for example, for fabrication of quantum machines, there are many questions that how to do that, how to. So that's one important area. And of course, people are talking about quantum machine learning, and there are algorithms for that. So it's a very fast growing, as your FDP is on emerging technologies. It definitely qualifies for as an emerging technology, and I'm talking on that. But at the same time, we should also remember as teachers that this is not the only thing. Like, this is emerging technology. There is trust on this. There is funding on this. We should not forget the our technology, because that technology, the usual standardized technology, because that there is need for research on that, and more than research, there is a need for understanding of that. Sometimes I see that these things like quantum computing and all that, they are now something like buzzword in different communities, and people are kind of like, you are listening to me for talking about um, quantum computing, but you will not listen to me if I say that I am going to discuss about block ciphers or SBox design, and you say that, okay, already it's all standardized. Why do we just discuss about that? You will not listen to. I mean, I'm not talking about you. I mean, like, so this is a trend. Like, I'm also talking about quantum computing, but I'm not talking about the structure of DS, because we will say that DS is dead. I mean, like, it's for 20 years it's out of the standard. But how far we do know about how to develop indigenously develop block ciphers? We don't know most very much. So that is not very catchy, but that technology is also very important. So this is what I'm saying. I'm talking about quantum computing, but I'm just putting a warning sign that we have to take a diverse view on everything. I mean, like, we have to actually know things very well, and that need not be only emerging technologies. We have to also put enough emphasize on standard technology. So that's important, because see, and like, if you talk about disease, people usually die of either curable disease than incurable disease. Now we have a incurable disease and people are dying, but usually people die of rare disease don't occur very much. So we have to know how to diagnose the disease those that can be cured rather than disease that cannot be cured. So it's like that. Mhm. Okay. Okay. Thank you very much. Okay. All right. Of course. Like, it's only future. Quantum computing is basically future, only future scope. I don't see a lot of immediate scope. Of course, immediate scope is there, but the most of the scope is in the future. So I mean, people who are working for quantum computing and these kind of things, they are looking at future more than the present. Okay. Yeah. Thank you. Mm. Okay. Bye bye. Thank you then. It was good to interact with you, and so bye bye.
Sir, if a problem is happening in that present time, then it will shape that. Uh,
Good morning, everyone. The next session as a research person, Dr. Debashish Chakravarty. So the next session is by Dr. Debashish Chakravarty, Associate Professor Mining Engineering, IIT Kharagpur, and his topic is AI and now a brief introduction about Dr. Chakravarty. His research area is slum mine mapping and locational surveillance using digital photogrammetry, geo-resource exploration using geoinformatics and GPS and GIS, mineral resource mapping using geodesics and INSAR technology, geotechnology and numerical stability analysis of slopes. Again, also hyperspectral imaging identification and resource robotics, risk robotics and robotic mapping, aerial UAV and terrestrial. He got a German government fellowship for postdoctoral research in 2001. He handled many projects from ISRO, CIL, R&D board, MHRD, etc. He's also done consultancy projects for JPL, JSPL, Tata. He has more than 25 publications, different journals and conferences. So his topic is AI and robotics. So some concept on the AI and robotics. But as per Wikipedia, there are some other type of definition given. Artificial intelligence or AI is intelligence demonstrated by machines, unlike the natural intelligence displayed by humans and animals. Its environmental and takes actions that maximize its chance of successfully achieving its goals. The term AI is often used to describe machines or computers that mimic cognitive functions humans associate with, such as learning and in the context of the robotics. Robotics is an interdisciplinary research area at the interface of computer science and engineering. So in the interdisciplinary, you are also getting many departments, mechanical, electrical, computer science, electronics. So many are involved in developing the robotics. Robotics involves design, construction, operation, and use of robots. The goal of the robotics is to design intelligent machines that can help and assist humans in their day-to-day lives and keep everyone safe. Robotics draws on the achievement of information engineering. So now I hand over the session to Dr. Chakravarty on the topic artificial intelligence and robotics. Welcome, sir, for the session.
Hello, am I audible?
Yes, sir, audible, sir.
Okay, good.
Good morning, sir.
Good morning to all of you and the organizers as well as the participants. And thank you to Dr. Shekhar for a nice introduction on the topic and also of me. I to just introduce myself. Is my presentation viewable to all?
Yes, sir.
To introduce myself, I think most of it has been done by Dr. Shekhar, and I, Debashish, working as a professor with the Department of Mining Engineering, IIT Kharagpur. And the confusion majorly I face is, people with some old IT page and still put it associate, that's fine. For almost 3 years it is an professor's position. So I completed my BTech, MTech and PhD from the same institute, IIT Kharagpur, BTech in 93 and MTech and PhD following the 95 and then 98. So after that, I went for some job in PricewaterhouseCoopers where I used some of the data warehousing and data mining concepts, and then went for postdoctoral fellowship in Germany, where my work was in the Department of Applied Mathematics with the Computer Science Division, where I worked on collaborative and distributive, virtual and virtual reality modes, augmented reality modes. And then I joined back the same department in 2003. So I work in the area of some basic hardcore mining engineering of rock mechanics, surveying, mapping, numerical modeling, visualization, and some interdisciplinary aspects of innovative technologies or innovative mining technologies which have come to be very much useful in these days. And those cover the areas of robotics, AI, rescue robotics, mapping, simultaneous localization, all those tasks. So today I welcome all the participants when I will take you through my series of slides, and this will definitely not be so theory intensive, because if I want to cover the theory, it might take several hours, or even each of the small topics are very dedicated topics of research and frontier research, where lot of people are working in the academia and also in industry. Actually, we are in the age of information age, where we earlier used to have less amount of data, but now we have huge amount of data with different velocities and atomicities and quantities reaching us every moment, being collected from one or the other type of sensors, or even social or other type of networks through use of human uses. So we have lots of availability of data. So the next thing is, how do we use this data to our benefit? That's where a lot of applications of data science, evolutionary computing, ML and DL and AI related stuffs come into play. This is where the existing state of the art stands. And once I try to see them in reality, so there is a basic difference in the theoretical research, and there is another whole group of efforts that go ahead in terms of getting them implemented. So field research. So we are working in the areas of high-end theories as well as putting them into reality. So how do we get to know both of them to get the work done? And one of the most important aspects which have come in the recent days, which we all know, is automation. So any autonomous system which has some or the other utility, even very useful in the present day of global pandemic, where people are not willing to get in touch with or close with any other human being. So there we would be willing to have the use of autonomous systems. So these are actually, I say, sensor-based, data-driven systems, and the most common example of them come in the form of robots. And as Dr. Shankar was telling, there are lots and lots of schools of thoughts existing. So I will take you through through the basic interesting features, and in some places I'll take you through the aspects which are developing, which are existing, but I will not go to the mathematics now because it's difficult to be covered in this class. So the organization, I will take up first an overview of the AI and intelligent systems, some of the possible very upcoming research areas, and we will take up some examples of agent-based environments concept or popular search algorithms. Followed by that, some discussions on fuzzy logic, neural networks, and NLPs, expert systems, and I'll take some deep into the robotics. We'll take up some questions if there are any. So if I start to talk of the overview of AI, what is AI? The science and engineering of making intelligent machines, especially intelligent computing programs, were earlier days thought of as AI. And this artificial intelligence is a way of making a hardware, a computing device, or a computer controlled robot, and an intelligently thinking software work synchronously in a similar manner as that of human, as that of human thinking is, or human processing is. So we are trying to reach the human level of decision making or human level of performance by the use of some, mm, some hardware and some software. So this is accomplished by studying first how the human works, how the human brain thinks, how the human take decisions, and how they work while trying to solve a problem either in a standalone mode or in a network or group mode, and using the inferences, using the outcomes as the basis, they try to develop intelligent softwares or intelligent systems, or together a setup which can work together. So if this is what is the broad arena of AI, then I can talk of the basic philosophy that while exploiting the power of computing devices or computer systems, the excitement or the curiosity of human led to some wonderful, you know, thoughts. Can machines think and behave like humans? All of us know the story of Sophia, the first non-human citizen in the world. So can machines think like human? We have over the years. So over the years, there are whole group of scientists, researchers, field engineers working together to achieve those goals. So we can classify the goals of AI as broadly to into two classes, maybe to come up with some setup or system which can take experts position, so they can create expert systems which can exhibit